Hi everyone, today we're going to study similar figures. Two polygons of the same number of sides are similar. We have two conditions. If, first condition, their corresponding angles are equal. Second condition, their corresponding sides are in the same ratio or proportion. Example 1, we say that all squares are similar. Letter B example, all equilateral triangles are similar. Letter C example, all circles are similar. Example 2, we have these two figures. We can observe that these two quadrilaterals are similar because all the corresponding angles are equal and all the corresponding sides are in the same ratio. That is 2.4 is to 4.8, and that is equal to 2.1 is to 4.2. Example 3. We have these two figures here. We can observe that these two parallelograms have equal corresponding angles. All angles are 90 degrees. But corresponding ratio of sides are different. So we can write 3 over 3 is not equal to 3 over 3.5. Therefore, they are not similar. Example 4. We have these two figures. The two polygons have different shapes, or we say that corresponding angles are different. So, they are not similar. Hi everyone, today we're going to study similarity of triangles. Two triangles are similar if we have these two conditions. 1. Their corresponding angles are equal. Second condition, their corresponding sides are in the same ratio or proportion. Note that if corresponding angles of two triangles are equal, then they are known as equiangular triangles. A famous Greek mathematician, Thales, says the ratio of any two corresponding sides in two equiangular triangles is always the same. Let's go to basic proportionality theorem. If a line is drawn parallel to one side of a triangle to intersect the other two sides in distinct points, the other two sides are divided in the same ratio. Example, we have this triangle ABC. Suppose we have this line that connects the sides AB and AC at the points D and E respectively. Also given here that the side DE is parallel to the side BC. And from here we can write AD over DB equals AE over EC. This is the converse of that theorem. If a line divides any two sides of a triangle in the same ratio, then the line is parallel to the third side. Example 1. if a line intersects sides AB and AC of a triangle ABC, as shown here, at the points D and E respectively, and is parallel to BC. Prove that AD over AB equals AE over AC. Using the theorem, we can write AD over DB equals AE over EC. We can take reciprocal of our ratio. So we write DB over AD equals EC over AE. Let us add 1 to each side and simplify. So it becomes like this. When we simplify, the left side becomes DB plus AD over AD equals the right side EC plus AE over AE. Now look at our figure. In the first fraction here, the DB plus AD, it is DB plus AD. We can simplify as the side AB. So AB over the denominator AD equals the right side EC plus AE. We can simplify as the side AC. So we write here AC over the denominator AE. Then we take reciprocal. It becomes AD over AB equals AE over AC. Now we are done. We are able to prove that AD over AB equals AE over AC. Example 2. ABCD is a trapezium with AB, the side AB, is parallel to the side DC. The points E and F are points on non-parallel sides AD and BC respectively, such that EF is parallel to AB. Show that AE over ED equals BF over FC. This is our figure. We can write AB is parallel to DC and is parallel to EF. This is given in the problem. Let us draw a line connecting the points A and C. This line will intersect the line EF at the point G. Now, look at the triangle ADC. With our theorem, we can write AE over ED equals AG over GC. Let this be equation 1. We have another triangle in the triangle ABC. So we can write, based on theorem, CF over FB equals CG over GA. Let us take reciprocal and let us rearrange. So this becomes BF over FC equals AG over GC. Let this be our equation 2. Now notice the equation 1 and equation 2 together. We can say that AE over ED equals BF over FC. Now we are done. We are able to show that AE over ED equals BF over FC. Example 3. Given that PS over SQ, these are sides of this triangle, equals PT over TR, and the angle PST is equal to the angle PRQ. Prove that triangle PQR is an isosceles triangle. By the theorem, given that PS over SQ equals PT over TR, then the side ST is parallel to QR. Therefore, the triangle PST and triangle PQR are similar. In that case, the angle S is equal to the angle Q. We say that corresponding angles are equal. In the given, it says the angle S is equal to angle R. And now we are telling that angle S is equal to angle Q. It means the angle Q is equal to the angle R. Then we say that the side PQ is equal to the side PR. Remember the rule that sides opposite equal angles are equal. Therefore, the triangle PQR is an isosceles triangle. Hi everyone, today we're going to study criteria for similarity of triangles. In the beginning, we know that two triangles are similar if their corresponding angles are equal. And the second condition, their corresponding sides are in the same ratio or proportion. Look at these two triangles. We say that angle A is equal to angle D. Angle B is equal to angle E. And angle C is equal to angle F. Also, side AB over side DE is equal to side BC over side EF is equal to side CA over the side FB. Then the two triangles are similar. Let us see this theorem. If in two triangles corresponding angles are equal, then their corresponding sides are in the same ratio or proportion, and hence the two triangles are similar. This criterion is referred to as angle, AAA, criterion of similarity of two triangles. We have this example. When we see that angle A equals angle D, also angle B equals angle E, also angle C equals angle F, then immediately we can conclude the two triangles are similar. This is now the simplified AAA criterion. If two angles of one triangle are respectively equal to two angles of another triangle, then the two triangles are similar. If two angles of a triangle are respectively equal to two angles of another triangle, then by the angle sum property of a triangle, their third angles will also be equal. This may be referred to as the AA similarity criterion for two triangles. Look at this example. When angle A equals angle D and angle B equals angle E, then we can conclude the two triangles are similar. Here's another theorem. If in two triangles, sides of one triangle are proportional to, that is, in the same ratio of, the sides of the other triangle, then their corresponding angles are equal, and hence the two triangles are similar. This criterion is referred to as the side-side-side SSS similarity criterion for two triangles. Example, we have the two triangles here. Since 3 over 4.5 is equal to 6 over 9 and also equal to 8 over 12, then the two triangles are similar. Here's another theorem. If one angle of a triangle is equal to one angle of the other triangle, and the sides including these angles are proportional, then the two triangles are similar. This criterion is referred to as side-angle-side SAS similarity criterion for two triangles. Example, we have the two triangles here. We can see that angle A is equal to angle D, both equals 50 degrees, and 2 over 3 equals 4 over 6. Then the two triangles are similar. Example 1. In the figure below, if side PQ is parallel to side RS, this is the PQ and this is the side RS, prove that the triangle POQ is similar to the triangle SOR. Given is the side PQ is parallel to the side RS. If that is the case, the angle P is equal to the angle S. Also, angle Q is equal to angle R. That is because the angles are called alternate angles. Also, the angle POQ is equal to the angle SOR. The two angles are what we call vertically opposite angles. Therefore, the triangle POQ is similar to the triangle SOR by virtue of the AAA similarity criterion. Example 2. Observe the figures, then find angle P. In the figure here, this is the angle P. Note that the side AB over RQ is equal to 3.8 over 7.6, and this is simplified into 1/2. Also, the side BC over the side QP is equal to 6 over 12. When we simplify, this is 1/2. The side CA over the side PR is equal to 3 square root of 3 over 6 square root of 3. We can simplify this as 1/2. Therefore, AB over RQ equals BC over QP equals CA over PR. Therefore, the triangle ABC is similar to the triangle RQP, that is SSS similarity criterion. Therefore, the angle C is equal to the angle P because the two angles here are corresponding angles. We can see that we can solve for angle C in this triangle. We know the formula that angle A plus angle B plus angle C equals 180 degrees. We can isolate the angle C in the left side. So we have 180 degrees minus angle A minus angle B. We have the values for angle A and angle B respectively. We substitute it here. So it becomes like this, and then we simplify, the right side becomes 40 degrees. This is angle C. This is the same angle for angle P, that is 40 degrees. Example 3. A girl of height 90 cm is walking away from the base of a lamp post at a speed of 1.2 meters per second. Look at the figure here. If the lamp is 3.6 meters above the ground, find the length of her shadow after 4 seconds. From the figure, you can see that DE is the shadow of the girl. Let DE be x in meters. So we write here x. Now, BD is the distance from the base of the lamppost up to the girl after 4 seconds. Remember, in the given, the girl is walking at 1.2 meters per second. So for the 4 seconds, we multiply 1.2 meters by 4. That will be 4.8 meters. That is the length of BD. Now, in triangle ABE and triangle CDE, we can see that angle B is equal to angle D. Also, the angle E is equal to angle E. Note that angle E is common to the two triangles. So, the triangle ABE is similar to the triangle CDE, and that is AA similarity criterion. Therefore, BE over DE equals AB over CD. When we substitute the values, we will have like this. For the BE, that is 4.8 plus x over DE is x equals AB is 3.6. That is the height of the lamp posts. And CD is the height of the girl in centimeter. It is written here 90 centimeter. When we convert this into meters, we write 0.9. On the right side, we can simplify the fraction into 4. Now we cross multiply x to the right, we have now 4x. We transpose this x to the right, it becomes negative x. So 4x minus x will be 3x. From here, we divide the equation by 3 to get the value of x. So that will be x equals 1.6 meters. So, the shadow of the girl after walking for 4 seconds is 1.6 meters long. AB. First given here is the line segment XY is parallel to the side AC. Then the angle BXY, this is the angle, is equal to the angle A, and the angle BYX, this is the angle, is equal to the angle C. We call them corresponding angles. Therefore, the triangle ABC is similar to the triangle XBY because we have AA similarity criterion. So, by the theorem, the area of the triangle ABC over the area of XBY is equal to the side AB over the side XB, and that is squared. Let this be equation 1. Now we have another given. The area of the triangle ABC is equal to twice the area of XBY. So we rewrite this as area of ABC over the area of XBY equals 2 over 1. Let this be equation 2. When we equate equations 1 and 2, we will get the square of the fraction AB over XB equals 2 over 1. Then let us take square root of both sides. The square of the left side will be cancelled out. And then on the right, we will have square root of 2 over square root of 1, which is still 1. And from here, we will take reciprocal. So on the left, we have XB over AB equals 1 over square root of 2. From here, let us subtract each of the side from the value 1. We have on the left 1 minus XB over AB equals 1 minus 1 over square root of 2. When we combine the left side and the right side as one fraction, the left side becomes AB minus XB over AB equals, the right side is now square root of 2 minus 1 over square root of 2. Now let us look at the graph. In the numerator, it says AB minus XB. We can see that the value is AX. So we change the numerator by AX over the denominator, same AB. We copy the value of the right side. Then let us rationalize the value of the right side. We multiply this by square root of 2 over square root of 2. So it is simplified as 2 minus square root of 2 all over 2. So this is now the ratio of AX over AB. This is our final answer. we have this triangle ABC. We have a right angle on the angle B. Let us prove that the square of the side AC is equal to the square of the side AB plus the square of the side BC. Let us draw a line from B going to the side AC perpendicularly at the point D. Then the triangle ADB is similar to the triangle ABC that is based on the theorem a while ago. So we can write AD over AB equals AB over AC. We know that sides are proportional for similar triangles. When we cross multiply, the left side becomes the side AD times the side AC equals the square of the side AB. Let this be equation 1. Also, the triangle BDC is similar to the triangle ABC. This is based on the theorem a while ago. So we can write CD over BC equals BC over AC. We know that sides are proportional for similar triangles. When we cross multiply, it becomes like this. Side CD times the side AC equals the square of the side BC. Let this be equation 2. Then let us add equations 1 and 2. So we have like this. AD times AC plus CD times AC equals the square of the side AB plus the square of the side BC. Look at the left side. There is a common value, and that is AC. We can factor it out, and it becomes like this. The left side is now AC times the quantity AD plus CD. From here, let us look at the figure. The AD plus CD is equal to the full length of AC. So we substitute it here. So the AD plus CD becomes AC. When we multiply AC by AC, we get the square of the side AC. And from here, we're able to prove the Pythagorean theorem. Let us see the converse of Pythagoras' theorem. It says, in a triangle, if square of one side is equal to the sum of the squares of the other two sides, then the angle opposite the first side is a right angle. Example 1. In the figure below, the angle ACB, this is the angle here, equals 90 degrees. And the line segment CD is perpendicular to the side AB. Prove that the square of the side BC over the square of the side AC equals BD over AD. In the triangle ACD is similar to the triangle ABC that is based on the theorem in the beginning. So we can write AC over AB equals AD over AC. We know that corresponding sides are proportional. When we cross multiply, the left side becomes the square of the side AC equals side AB times side AD. This is our equation 1. Also, we have this triangle BCD is similar to the triangle BAC that is based on the theorem in the beginning. So we can write BC over BA equals BD over BC. We know that corresponding sides are proportional for similar triangles. When we cross multiply, the left side becomes the square of the side BC equals side BA times the side BD. Let this be equation 2. We can combine equations 1 and 2 into like this. On the left side, the square of side BC over the square of the side AC equals BA times BD all over AB times AD. We can see that the BA is equal to AB, so we can cancel this and this. So what remains on the right is BD over AD. And from here, we stopped because we are able to prove that the square of BC over the square of AC equals BD over AD. Example 2. A ladder is placed against a wall such that each foot is at a distance of 2.5 meters from the wall and each top reaches a window 6 meters above the ground. Find the length of the ladder. Let us draw this figure and then we let the AB be the length of the ladder. CA is the wall and A is the window. From Pythagoras' theorem, we can write the square of the side AB, that is the hypotenuse, equals the square of BC plus the square of CA. Then let us substitute corresponding values. The BC is 2.5, then we square that, plus CA is 6, that we will square later. The square of 2.5 is 6.25, plus 6 square is 36, and the total is 42.25. But we want the AB, so we will take the square root of this value, and the answer is 6.5. Thus, the length of the ladder is 6.5 meters. Example 3. In the figure below, AD is perpendicular to BC. Prove that the square of AB plus the square of CD equals the square of BD plus the square of AC. From the triangle ADC, we can write the square of AC equals the square of AD plus the square of CD. This is based on Pythagoras' theorem. This is equation 1. For the triangle ADB, we can write the square of AB plus the square of AD plus the square of BD. Also, this is based on Pythagoras' theorem. Let this be equation 2. Then we subtract equation 1 from equation 2. The left side is now square of AB minus square of AC equals the group square of AD plus the square of BD minus the group square of AD plus the square of CD. We can remove the grouping symbol and change the sign of the terms of the second group. So it becomes like this. On the right, we can see that we have here square of AD minus square of AD. That becomes 0. What we do next, this negative square of CD, we will transpose to the left. This negative square of AC, we will transpose to the right. So, we have now square of AB plus square of CD equals square of BD plus square of AC. We're able to prove the problem here.